Good morning, good afternoon. On behalf of ASEE's Manufacturing Division, I'm so glad to introduce John Liu today. The first time this summer, ASEE 2024, we decided to have some guest speakers, and our inaugural speaker is John Liu from MIT. John has so much going on with the extended reality in manufacturing as a research, as a practice, as a teaching. So we'll learn his best practices today. The talk will take almost 40 minutes, then we'll open the forum for questions. Please mute your speakers, and then you'll have time to ask some questions. Thank you, John. The podium is all yours.
Thank you, Ismail, and thanks for having me, Manufacturing Division. I think it's a beautiful community, and I'm excited to talk about, kind of present on how we think about crafting XR experiences today. You may be wondering a little bit about me. I direct a group in learning engineering at MIT. My background is in mechanical engineering. I studied at the MIT Mechanical Engineering Department. And at this point, I lead a group in applying how we think about engineering into the learning of engineering. I'm also serving as the education and workforce lead for a new initiative at MIT, essentially for all things manufacturing, ranging from research, industrial policy, industry engagement, education and workforce, for the entire campus. And for that, again, I serve on the education and workforce side. So with that, let me start with some big picture data. The first is that in the US, employment in STEM has actually grown an incredible amount in the past 3 decades, 79%. And it's projected by the US Bureau of Labor Statistics that STEM-related occupations will grow at twice the rate of non-STEM occupations in the next 10 years. And so you might have seen some of these headlines in the news recently. So for example, chips to get to semiconductors, to rebuild that capacity in the US, they're looking at a need of 70 to 90,000 workers just to meet kind of the most critical needs. Similar to, for example, the submarine industrial base. Next 10 years, just to meet the most critical needs, they're talking over 100,000 workers in STEM. And then Boeing, who laid off a bunch of folks last year, is saying that they need to rehire a bunch of folks in engineering and manufacturing. And so we're seeing both these large level BLS data, but also industry specific and region specific surges in demand for workers in STEM. So it certainly begs the question, how do we scale STEM education and training? And then on another side, we see that a lot of other data that's quite concerning. The ACT, some of you, or maybe some young people that had to take the ACT exam to apply for colleges. So that organization has put out data that essentially only 20% of high school graduates are actually prepared for university level STEM courses. We see that over 40%, nearly half of students who declare STEM end up leaving before graduation. And then there are large disparities in the actual engineering student and workforce population. So, for example, here, whereas 50% of the total workforce is women, you only have 15% of the actual engineering workforce as women. And we see similar stark contrasts when it comes to across ethnic lines as well, and race lines. And so it begs the question, how do we improve STEM education and training? So twofold question: scaling and improving. And the analogy I like to draw from is actually that of history and how we've seen progressions of educational technologies improve. So you had, for example, YouTube, which many people don't associate with educational technology, but at this point, many people use YouTube as a way to learn how to fix their car, or as a way to brush up on, a particular mathematical concept that they didn't understand in class. And so the advent of on-demand video actually really opened up access to education and learning, but more than 2 decades ago. And with the access of on-demand video, then you had developments like Khan Academy, where you were able to access high quality, free instructional videos, and really to anyone around the world. When you pair up this kind of on-demand video with computer grading, that's what led to flipping the classroom, where you're going from a traditional lecture format to homework activities to now doing lecture at home and classroom activities in the lab, in the classroom. And so we see how progressions of educational technologies have led to actual innovations in pedagogy and andragogy. And so what's interesting in 2024 is that XR has actually progressed. And so it begs the question, certainly, do we see a similar excitement and potential through XR? And so one of the reasons why it's very interesting is, as you've all seen, it's become a hot topic within the public and maybe in our space. But whereas there's a bit of a dip in the past few years, Meta killed their metaverse, initiative, et cetera. But in this year, it's become a hot topic again with large tech companies. And in fact, just last week, Meta announced the launch of a new eyeglasses, essentially, that are smart and have AR and MR capabilities. And you see NVIDIA with their Omniverse initiative. So many large tech companies this year are becoming a lot more interested in AR, VR, and XR again. We, of course, have seen how LLMs have recently been introduced into the school, and how they've radically changed the nature of teaching and learning. And then adoption is still mixed across broad society, but within the young population, it's getting higher more and more. And so today you'll see 1 in 4 teens already play in VR headsets. And in fact, when we demo some of our things to young students, like in high school or junior high, there's a lot of folks who get really excited and potentially about manufacturing just because they've already been in an Oculus headset, for example. So my group, what we do is we seek to solve challenges in learning to better meet the demand of STEM competencies. And we do that in a kind of threefold effort. We start with learning sciences, looking at how learning actually happens in different environments and how people learn STEM. And then we seek to apply it to educational technologies with a focus in extended reality. And we're looking for impacts along a number of different levels, from the individual, the school, the community, and industry. And so hopefully in today's webinar, you'll be able to see that kind of range of impacts through the different projects that we've been able to launch so far. And then, as Ismail mentioned, after kind of serving some of the projects in certain past and active projects in my group, I'm hoping to finish with just some of the takeaways that we've had recently and some of the exciting directions I see XR and learning go in this year and the following years. Okay, so the first project I want to share about is actually one that was associated with my first publication in ASEE back in 2021. And this one is centered around a pedagogy called Disassemble, Analyze, and Assemble, or I'll call it DAA activities for short. Now, this pedagogy is really, and this is a picture of my classroom in 2008, which is essentially the capstone manufacturing course for juniors and seniors of mechanical engineering at MIT. And what we do every single week is we pass around products for students to tear down, and we lead them along a series of guided questions in order for them to learn and apply manufacturing analysis. Now, that's been around as an industry practice for decades, for cost analysis, for benchmarking competitor products, for ideation and brainstorming. But as a pedagogy, it's really only been formalized in the past decade or so. And we've seen in the literature that DAA is associated with improvements along a number of different sorts of learning, like design thinking, systems thinking, even just the enjoyment of learning manufacturing and engineering. But the challenge with this pedagogy is threefold. First, what if I actually want to be able to teach learners around the globe? I certainly can't, it's challenging to ship kits, to Bangladesh or to Japan. And then the second one is, what if I want to teach objects that aren't easily disassembled on the desk? What if I want to be able to teach engineering principles, design principles around a nuclear reactor or a windmill turbine blade? And then finally, it's an issue around uniform guidance, that when I walk around the classroom, I may have the Socratic method. When another colleague walks around, maybe they're giving away answers directly. And so there's certainly a question around how do we actually give both high quality guidance, but also to make sure that it's uniform. And so this certainly raised the question for myself and my team, could augmented reality, AR, be a potential solution? It's 3D, it's in your physical context, it's scalable, it's interactive, and perhaps you only need a smartphone or a tablet to use. Now, one of the interesting parts of the literature is that actually for much of XR applied to learning STEM, we see that it's primarily been used for lower level cognitive thinking. And so those of you who, and I'm sure most of you teach your own engineering courses, you might have remembered Bloom's taxonomy, where lower level cognitive skills are associated with fact recall or memorization. Higher level cognitive thinking is associated with applying, evaluating, debating, etc. And so a lot of XR really has still been used for, recalling facts or remembering things. And then finally, there's a whole area of research when it comes to scaffolding guidance. Could we apply some of that literature into our work? And so this is an interesting design space for us. Can we merge DAA pedagogy with AR so that we can support learners to learn how to analyze in manufacturing contexts and thereby push up the level of cognitive skills? And so if we combine the two, perhaps it yields a number of different questions that we have. One, do students perceive their learning of manufacturing analysis using DAA, AR-assisted DAA to be valuable? Two, can students use AR DAA to make meaningful conclusions in engineering analysis? And then finally, what principles might assist our design of AR and the application to support learning this kind of pedagogy? Using this pedagogy. Okay, so here's a demonstration of the version 2 application that we actually created, my group created. And you can see everything here is, physical, the table, the plant that you're seeing, even the QR code, but these models of the mass-produced electronic tablet are virtual. And so you can see very high fidelity models. And then maybe I actually want to come in and examine one part. And so I can actually select a part and then look at it. You can even look at, machining marks that were applied post-process to be able to handle issues with the surface finish here. And then, I'm going to pause here for a second. Here is what to basically replicate what I might do if I were teaching a student. So if a student, is looking at this, a novice doesn't know what features are relevant and how to make meaning of those features and to connect it to relevant information about the manufacturing processes or DFM principles that they might be learning in class. And so what I might do in class is I might point to a particular area and say, hey, did you notice anything in this area? And what this app is able to do then is if a student needs more guidance, maybe they can ask for more guidance, and then these yellow boxes appear, cluing them or nudging them to pay more attention to those regions. And if a student wants even more guidance, they can click and hold on one of these yellow areas, and then you can see it will go to an actual text or a visual clue. And so we've now launched this app in an edX course a number of times, but at this point, it's been used in our edX course to teach students around manufacturing assembly and cost in particular. And what we did was we had students reflect on the activity, and then we developed a code book, just a tool in qualitative analysis, to be able to analyze the kind of reflections that students were giving us, to be able to analyze what kind of learning students were having when they were engaging in this activity. And here you're seeing just the structure of the code book here. And so we had multiple raters, and so we looked at inter-rater agreement. I'm just mentioning that there was a fairly high inter-rater agreement. And so let's get to those research questions that we asked in the first place. First, do students perceive that learning manufacturing analysis using AR is beneficial? And we saw that over 80% of learners perceived that it was valuable, with comments like, oh, I'm able to perceive and see the fine details of an object, even though I don't have it. Or, oh, I can understand each component, even though I can't touch it physically. The second question, can students use AR/VR to make meaningful conclusions? We were seeing students say, hey, because I can see and view and understand the internal features, that helps me understand the prototype better. Or, oh, now that I've seen the step-by-step disassembly, I can better visualize and understand the process of assembly. And seeing how all of these parts and assemblies came together helped me understand better this complexity of the product and appreciate the real-world significance of what I'm learning. So we saw more connections to product design and manufacturing assembly, less to some other topics that we were trying to teach, like processes and cost. And then finally, the question was, what principles assist the design of AR to support learning DAA? And here we derived a number of different principles. The first one is, often in XR, there's an emphasis in the designer community of relevance over realism, meaning it doesn't have to look exactly like it as long as I am able to convey the main idea. But in this case, when you're employing DAA pedagogy, it's actually the little features that you're trying to get and the detailed features that you're trying to get students to understand through DAA. And so, again, students were pointing out, oh, this tiny detail like an injection molding gate, or this particular overhang, right? So it certainly asked the question for a designer, what visual features could AR offer that would not be available by non-XR or physical DA activities? For example, could we actually implement CT scans or X-ray scans? Things that aren't necessarily normally associated with DA activities. And then another principle was we should really take advantage of the relationship between exploration and elucidating these physical relationships between the components, right? So we had students say, oh, we can see the connections between components without touching and seeing it physically. And so in our version 2, which I showed in the demo video, we had a kind of a scripted way of disassembling. You were pressing next, and every single time you could remove another sub-assembly. But certainly, begs the question in the future, actually, can students make richer insights on product design and systems if the app actually enables open-ended disassembly instead of scripted? And then finally, and this is not something that we were setting out initially to do, we initially thought that AR is a learning tool, right? It's a way that learners can engage with to learn manufacturing principles and analysis. But then we saw comments like this, which is, oh, this is so exciting for me because AR, I was going to use, or I know I'm going to use AR and VR in the future in my actual work. And so there's a link to authentic engineering tasks as well. So there's AR and VR as the learning tool, but then there's AR and VR as the engineering tool. And so it certainly begs the question, can we form better connections between learning your XR and shaping attitudes towards the future of STEM? So in conclusion, on this part of the project, we designed the AR app so that users can engage with learning manufacturing via this pedagogy DAA. We developed a codebook to analyze how students are experiencing and engaging AR DAA. And then we demonstrated scalability by releasing it into a MOOC and then analyzing how they actually engaged with this experience, finding positive hands-on learning experience and meaningful engineering insights. And then we've also extrapolated some principles on designing this AR specifically for learning using the DAA pedagogy. And for this one, a few years ago, we were awarded both the Best of Manufacturing Division and also Best of PIC too. And for more information, obviously, feel free to take a look at Welsh 2021. Okay, so that was the first project I wanted to share about AR product teardown. I'm going to go very brief in this one because I want to spend more time in the next one, but we're also looking at how people are learning micro nano skills as well. And so here, as many people know now through CHIPS, nanotechnology, huge, workforce is massive, but there's a number of different learning challenges associated with learning micro nano skills. One, a lot of our intuition on how objects actually interact with each other break down at the scale of the micro nano. And so, for example, van der Waals forces and a number of other types of forces that might come together at play. There's a number of significant dollars and costs that are associated with the laboratory, and that ends up limiting student time and student engagement, right? You might have, for example, a cohort of 10 students all surrounding one piece of equipment because it's too expensive, and then only one student is interacting with a piece of equipment. And so the goal is, how do we actually get to the point where we can actually engage students and better use their time using creation of interactive multimodal experiences? So here is just a range of different activities that we've designed. There are a range of computer simulations with haptic experiences and also AR/VR on the bottom left, where we're kind of opening up the scanning electron microscope to be able to show students what is on the inside and connect it with the mechanical and electromagnetic phenomenon, so that when they're looking at a screen, and that's really what they're mainly interacting with, they actually understand what is happening in the SEM. And that's a wonderful kind of affordance that augmented reality gives us. And we've published on all of these different, I won't go into all the details, but we've published it in ASEE, this kind of range of different educational experiences that we've created here. And so I'll just highlight a couple pieces of work here. The first is, we'll look at cognitive gains. Like, obviously, what do you know before and after, and how does it compare if you went the traditional paper route versus if you, for example, in this case, learned using haptics and visualization. We also look at learning preferences too, like how do students prefer to learn? And we're getting these very strong kind of preferences for simulation or AR over the handout. And we even had, a grad student who was already using the AFM for his research say, hey, this was so valuable for me. I wish I had this when I was starting my research in the lab. In fact, can you get this in the welcome packet of, every PI whenever you say, image this thing for the first time in AFM? So those are the kinds of things that we're looking at in micronano. And now I'm going to pivot to look at manufacturing hands-on fabrication skills. So we're interested also in how people pick up manufacturing hands-on skills, like operating a manual mill. Now, VR is also a very, very interesting route because you can forego issues of safety, you can get to issues, you can kind of forego scale, perhaps, you can introduce, you can engage and excite young folks. And so we started to explore this as well. Now, there are a number of, like, everyone's doing VR training these days. There's, I think there's something like 10 or 15 different commercial VR welder training systems out there right now. The problem, though, is with many of these commercial systems, the experiences are very, very scripted. So, for example, in this case, if you were learning how to set up a manual mill, it might take you to first to highlight the brush, and that's the only thing you can pick up in that moment. Once you pick it up, then it highlights the vise, and the only thing you can do at that point is to brush the chips off the vise, and then etc. All the tasks could be gated one by one, and once you go through this linear process, the simulator calls you quote unquote trained. But the issue is that a lot of how we learn is really not, a lot of how we accomplish tasks is not linear, and how we learn tasks is not linear either. There could be a number of different ways to accomplish the successful task. And so what we did is we actually went to kind of survey and benchmark a number of the different commercial VR simulators out there right now. This is something that well, it's in press right now. We're going to be publishing in IEEE ISMAR, which is one of the AR/VR conferences that IEEE puts on. And what we're finding is that across a number of different kind of aspects of open-endedness, from learning pathways to can the user choose how they're interacting with the system? Does the system adapt to the user's skill level? And can you pick different goals in your learning? On a number of different aspects of open-endedness, we're seeing that systems are fairly close-ended. There's not many systems that are considered very open-ended. And so to go back to this example that I showed you, an example of open-endedness would be, to kind of recognize the reality that, oh, actually, there's vice setup, which has a somewhat linear pathway, but with Chuck's setup, you can do it in any particular order. And that would extrapolate to all of the different tasks, in fact, within the, the machining setup for a drilling operation. And and I'm going to take a look. I see. Okay, so Fashiar has just asked to complete a survey. Please do that as well. And so if we look at, so in the top example, you would only have one pathway to successfully complete the task. On the bottom example here, there's actually over 1,000 ways to get to the end and successfully complete a drilling operation on a manual 3-axis machine. And so it's a wildly different way of learning, a wildly different way of interacting. And our work here then is to be able to create environments in VR that are so open-ended that a student can actually learn by making mistakes and by exploring. And so what you're seeing here is a user who can do a lot of different things. Now, obviously, we're grouping it by tasks so that you can understand what they're doing, but they can pick up the block, or they can pick up the drill, or they can pick up the chuck. And then the machine is responding to the user in the way that in the real world, where the system is telling you, oh, in this case, like you tried to set up the chuck without actually actuating the pneumatics. You got to go back, or you didn't bring in the chuck key, or you didn't take off the chuck key after you set it up. So it can actually respond to you because you're able to do many different things and be able to respond to the errors because you can actually make mistakes in this kind of environment. I'm not going to go through this entire demo video, but hopefully you get the sense here. And so we launched this pilot in our essentially freshman, sophomore class that introduces machining. It's a very short course. It's usually offered in January or the summer. It's just across 3 or 4 days, but we're trying to introduce them to machining tools. And so we have a range of different, machining experience and class standing. And then we did A/B testing essentially, where one set went through the regular or the traditional set of materials, and then one actually went through this kind of VR experience here. And what we're finding is that across a number of different, I guess you could say, categories of outcomes, from psychomotor, affective, and cognitive, we were seeing interesting gains. So on psychomotor, we were seeing that the VR cohort successfully completed the drilling task at a higher rate. They were committing less severe mistakes. They were asking less questions when they were actually doing the physical, like we threw everyone into the machine shop, whether they had done it before or not, to kind of see the efficacy of the training. And they're spending less time, those who went through the VR training instead of traditional. We also saw gains on the cognitive too. We quizzed them before and after, and we're seeing increases in better understanding with safety or setup and operations, et cetera. And we did also demo this at ASEE Con earlier this year. We were a demo finalist for this type of work. So that is just a kind of a snapshot of some of the projects that we're doing right now in my group at the MIT Leap group. And now I want to kind of take a step back and think about, what are some of the lessons that I and my group have learned over the past few years when we're thinking about designing effective immersive learning. So the first point is really from a kind of a design perspective. How do we design these things? And for those of you who are starting to explore or who have been designing AR VR experiences, I think the first place to start always is, what are my learning objectives? Do I care about someone able to set up a machine? Do I care about someone to troubleshoot a machine? Or do I think about analyzing or applying a particular type of analysis, right? So really thinking about your learning objectives and starting there instead of starting at the content. The second one is, what are my practical constraints, right? So how much time do I have? What headsets maybe do I have access to? What accessibility concerns do I have on the student progression or bandwidth of internet? And then finally, what are the affordances of the technology? So can it overlay visualization on my actual physical space, or am I thinking about a virtual space? We'll have to think very clearly about the learning affordances of that technology. So let's kind of take it through one by one a little bit more deeply. So on the learning objectives, many of you are familiar with Bloom's taxonomy. I referred to it earlier as well. So thinking through, is it really that I just want them to recall facts? Do I actually want them to explain or draw connections or produce original work? How we have, what our learning objectives are will really shape then what kind of experiences that they will be having in the AR/VR environment, and then how do we assess? Now Bloom's taxonomy is well known. People are maybe less familiar with other taxonomies associated with other types of learning. And so you actually have taxonomies associated with attitudes or affective outcomes. So am I just aware of a setting, or am I motivated to invest, or have I internalized a belief? So you may have other learning objectives that are associated with attitudes. And then there are learning objectives associated with skills, perhaps. So am I just able to imitate if I see someone, or can I actually perform several skills in conjunction, right? So there's a gradation when it comes to psychomotor skills as well. And so thinking through these different learning objectives is going to be key in first how to craft these effective experiences. So on the practical constraints, I briefly mentioned this before, but how much time do I have in the classroom or in lab versus how much time might they spend at home or in the dorm? What's the background? Like, do they have experience with machining, or do they have experience with a headset and VR? Am I teaching? Is someone who's very familiar with VR machining teaching? And then, what kind of equipment do I have access to? On the affordances side, here's a bit of a primer, I think, on what I think is so powerful in XR. This major affordance that I would call that we would call presence. This actually came from earlier on when researchers were actually working on teleoperation, and the question was posed, could I potentially set up visualization and haptics in a system that is so realistic that the operator of the robotic arm feels like the arms are his or her own. And so the presence can be kind of broadly defined as the sense of being there. And there's a number of different powers of presence that XR can afford. The first one is that, especially in VR or AR, one can transport different objects. In VR, you're often being transported into another environment, like now I'm on Mars, or now I'm in the cell. But AR will transport objects into your space, like for example, the electronics tablet that you saw that was on the desk. One can avoid danger as well, right? I can be in a nuclear reactor, or I can be at a construction site without ever being concerned that I'm going to be harmed. I can change scales. I can think on the scale of a galaxy. I can think on the scale of an atom. And then embodying. So VR engages, or AR engages the entire body of movement. And there's a whole body of research right now around what we call embodied cognition. And so the body helping the mind to think and learn, and the mind helping the body to move. So if you think about how instructors, when we're talking about how a particular parameter is increasing, we might actually use our hand to go up. Or when we were teaching or learning freshman physics, we might have used our hand to understand the right-hand rule. And then to socialize. So there's a whole body of work in collaborating in XR environments, even remote collaboration. In fact, even PTC, which is a software provider, is working on collaborative CAD that can be accessed using remote. And so all of these types of affordances might lead you for the learner to actually better engage with your material and to persuade. And I would maybe one could consider engage and change minds as kind of like super affordances or resultant affordances. And I also think it's kind of potentially fun to put out some challenges, I think, for those of you who are in this space, to think about. But some of the challenges that I think are really interesting are, one, how do we apply the latest in the learning sciences and learning theories to the design of XR? And so this is an incredibly multidisciplinary type of work where you have to understand and work with folks who know the technology, who know how learning works, folks who can design instruction, folks who understand human-computer interaction, folks who can actually develop content. And there's a number of different theories in the past 10, 20 years that I want to point you to. We don't have time to go into it today, but I think if you're interested in this field, to go more and more into it. So Mayer came out with a theory of multimedia learning a number of 2 decades ago that's still being applied today, and also more recent ones that combine a lot of the different levels of learning outcomes that I mentioned before, ranging from affective to cognitive, and including things like cognitive embodied cognition. And so the second one is, how do we develop smarter XR systems to teach skills? So basing it on, personalized guidance on how we learn. I talked about embodied cognition. This is still an active area of learning. And then, equipment, like if we want to be teaching manufacturing skills, how do we actually train these smarter XR systems to be smart about that? To be able to not guide you to do something that would be dangerous to you. I think that's a key obstacle that we need to be able to tackle in order for these systems to be more and more able to be adopted in actual learning for manufacturing. And then, certainly, there's a lot of work even presented this past ASEE about, ways of decreasing hallucinations in our LMMs. Is there that kind of equivalent within learning manufacturing? There's a number of different barriers still to adopting XR into the classroom and lab. One is it still takes highly trained individuals to design XR, but like imagine a future where XR could be as easy to develop and design like Google Docs and Excel. The cost of headsets is still fairly high. It's definitely come down from the past, but like richer forms of haptics, like exoskeletons or smart gloves, those are still extremely expensive. And then we still have motion sickness and dizziness. That's still an issue. And then how do we embed authentic assessments? There's still a lot of work out there that just focuses on kind of student preferences. But there's a whole area of work right now on like, how do we embed assessments into experience? And students may or may not even know that they're being assessed. The wonderful thing about XR is that everything is digital at this point. Interactions, where the student is looking, what the student is doing. And so there's a whole area of opportunity here. There's always a question of, are they getting better at your AR/VR thing, or are they actually getting better at the authentic task? And so we have to be very really think critically about that issue. And then how do we translate outcomes from individuals' task or skills acquisition to actual programmatic levels, like upskilling entire cohort, or students being able to find a better job or apply, skills in their careers. And so we'd love to see greater connections to longer term and larger outcomes. And so here are just, some of the, a summary of some of the things that I'd love to see progress in XR and learning manufacturing. And with that, I'm going to thank you all for your attention and your attendance. I'm going to conclude with just a couple kind of announcements, since I already have the floor. The first is that manufacturing letters, which I'm sure all of you are familiar with, we are releasing a new special issue next year. And so there's a call that we haven't announced publicly, but I'm going to announce it to this group first, that we're launching a special issue in innovations in manufacturing education. Myself, Ismail Fidan, and a guy by the name of Peter Zink, who heads education at PTC, we're the guest editors. And I highly encourage you to submit for this issue. In fact, if you're submitting for ASEE Manufacturing Division, this year we have established a fast track from ASEE Manufacturing Division papers to this Innovations in Manufacturing Education special issue. But you can also directly submit a manuscript, if you like, to manufacturing letters. These are short papers, papers at about 1,500 words, but I would highly encourage you to consider. And if you haven't, submitted something, you're not planning on submitting an abstract, hopefully this will be a motivation to submit an abstract to manufacturing division at ASEE. Abstracts are due tomorrow. It's an abstract, and so it's a very short thing, hopefully a low lift. And the last thing is, I continue to love to kind of facilitate broader engagement with this community in our division. And so my lab is in Cambridge in Massachusetts. next time you're in Boston, please visit. Love to have you. And I am in the process of actively hiring 2 more postdocs. And so if you're interested in manufacturing education, STEM education, learning technologies like the work that you've seen there, or you have a student, or you have a student who's looking for a postdoc, please send them my way. So with that, I want to thank you for your time. It's been lovely to be in this webinar, and I'd love to take any questions for a wonderful discussion now.
John, thank you for attendees. Let's go ahead and ask some questions. We have almost 20 minutes, but we don't have to stay that much long. You know how to reach him after the webinar. You can go ahead and shoot him an email. I'm sure he'll get back to you too. In the meantime, after the talk, while we are fresh, go ahead and ask some questions, please. I see a silence. That means everybody's happy. No question.
Yeah, I have a comment, not a question. I mean,
Myself, go ahead.
Yeah. So, John, this is very good. I mean, I really enjoyed your work and the presentation. So, are you interested? I'm sure you are in presenting something in the Make It session at the ASEE Manufacturing Division this year, coming year.
Yeah, sure. I mean, we are always. I mean, I'm going to be there for sure, and then another member might come as well. I don't know if we have new work to present at the Make It session, but we are presenting some work already, and so happy to come and give a demo if people are interested in trying any of the things that we're already creating here.
Sure. That's yeah. So it can be something you already did. I mean, you just need to submit an abstract. We haven't created the session yet. We are working on it.
Okay, yeah. I mean, if it's like, hey, if people want to, engage with the VR heads, the VR training and like try out manual mill, or if people want to try out product air down or AR, scanning electron microscope, like I can just bring a headset and bring some tablets for people to try out. Like we have demoed, as you know, we've demoed in other places, and happy to demo more.
Yeah, that would be great. I'll follow up with you later.
Sure, yeah, happy to do so. And
John, before the webinar, I was looking at your IMTS talk with the creative talks, I believe, almost 20 minutes. There you have a very strong points about the MIT's manufacturing infrastructure. I'm sure a lot of us will enjoy hearing that. Would you please give us a short debriefing, the history to today, MIT's manufacturing infrastructure, so that we know where you are and now and how other schools can replicate?
Oh yeah, no, absolutely. So, and let me just throw into the Zoom chat the video that Ismail was talking about. So, as some context, just a couple weeks ago, I attended IMTS. That is the largest manufacturing trade show in North America, and by some years, I think it's the largest in the world. Every time they host it every other year. Every single time they host, it's over 100,000 participants, mainly for the industry. But what they had here was they were hosting interviews with particular guests. And so what I've posted is a YouTube video recording of my interview between myself, a conversation between myself and Chris Lukey. And one of Chris's first questions was, what is MIT's relationship or involvement with manufacturing? And I was just saying MIT has had a long history in manufacturing. And I would give 3 kind of examples. The first is MIT had the first demonstration of CNC machining just in Building 35, which is the building that I work in. I think this was back in, I'm kind of losing my dates now. The second is 3D printing was actually coined by Professor Ellie Sachs in a patent in the 1990s. Happy to share that, but Professor Ellie Sachs is also a colleague of mine. We just were chatting in the machine shop last week when he was coming through one of my classes. You know, and a lot of the kind of major, you could say some of the major additive manufacturing companies like Formlabs, Desktop Metal, Vulcan Forms, they all have a MIT connection, often formed by MIT alumni. And so kind of large contributions in additive manufacturing. And the final one, which is probably the one that this group is least familiar with, is back in, I think all of you are familiar with the US offshoring manufacturing activities starting in the early 2000s. Even in early 2000s, early 2010s, we had, you know, the head economist of the US government and other economists saying, this is the right way to go, innovate here and produce there. And MIT, I believe, was the first group that came out and challenged that notion back in the early 2010s when they launched essentially a campus-wide research project, like very coordinated from the top, broad collaboration between engineering, science faculty, and faculty in business and social sciences to be able to examine, you know, over 200 firms in the US, in Europe, and in Asia to actually look at, you know, what kinds of capabilities and what is the relationship between innovation and production. And the conclusion at that point, and this has been published in a book called Production in the Innovation Economy. It was written and led by a faculty by the name of Suzanne Berger. The conclusion at that point was that it's these two come hand in hand, and the innovation here produced there doesn't work. If you want to innovate, you need to produce in that country as well, because production is part of the innovation process. You won't be able to further, you know, there's so much know-how and new knowledge that's created when you actually figure out how to realize a product and produce a product at scale. And so that conclusion was broadly shared to the White House. I didn't have time, by the way, Ismail, to say all this in the interview, but the conclusion of that study was broadly shared to the White House back in 2012 and 13, which ended up kind of deeply influencing industrial policy to the point where in the recent years, you're seeing a lot of industrial policy come out in the first time, you know, for the past few decades in things like CHIPS Act and other acts like that. And so from the start, MIT has been kind of deeply involved. As you know, I am kind of very interested on the workforce and the learning side of the manufacturing picture. Great question, and thanks, Ismail. And I did post the YouTube link for other people who, you know, would like to learn other, you know, about MIT or our group's work in other aspects that we're involved with. Other questions? I know there's a number of folks on the call.
Hello, I am MD Fazil Rabbi. I have a questions. Like in your slide, maybe in the slide there was multimedia learning. Like how this multimedia learning is applied to the equipment, like AR equipment. Like, is it the multimedia learning is same as like the applications of multiple resource theory to multimedia?
Yeah, I'm not quite sure where I talked about. Oh, okay. I think it's about, are you talking about Mayor 2005? Where I was putting up a couple theories from
Yes.
the learning sciences. Yeah.
Yes.
So yeah, so multimedia here is really pairing up visual and audio, because those are the primary modes. Like when you are, for example, looking at a screen, right? Those are the primary modes of that you're receiving and interpreting information. Meyer doesn't include tactile information, though that would be another really interesting aspect as well. But just like trying to craft meaningful and effective experiences that combine visual and audio has quite a bit of work involved. Hopefully that question. And again, I encourage you to take a look. You know, you can definitely find Meyer 2005 multimedia learning everywhere. It's very, I don't know, there's like probably like 20,000 citations on this work. Meyer's pretty big in that space.
Okay, got it.
Thanks. Great. Well, thank you so much for your time, and I'll hand it back to Ismail for any other for any concluding remarks.
Oh, John, thank you so much. We appreciate that for being the first speaker for us. ASEE Manufacturing Division have a website dedicated to us. Our plan is to post the webinar there. You can go ahead and access later on because some of the attendees already questioning. You'll be able to watch and listen if you missed the chance to attend today. We'll have our second speaker early next year, and we will announce who and what topic will be for the second one. In the meantime, I'm glad we had John today. Tomorrow is the deadline for the abstract submission. Submit your work and submit your works for the, again, manufacturing special issue in the manufacturing letters. And we wanted to appreciate your attendance today. Thank you. Have a good semester too.